In this video, we will learn how to calculate the area moment of inertia. For an area, the moment of inertia calculated about any arbitrary axis, say axis AA, is defined as the integration of RAA squared times dA, integrated throughout the area. dA is the area of the differential element, and RAA is the perpendicular distance between this differential element to the axis AA. Normally, we would put this area into an XY rectangular coordinate system, and we are interested to find out its moment of inertia about the x-axis and the y-axis. So we pick a differential element with area dA at the location xy, and because its perpendicular distance to the x-axis is y, therefore its moment of inertia about the x-axis is the integration of y squared times dA. Also, because its perpendicular distance to the y-axis is x, therefore its moment of inertia about the y-axis equals to the integration of x squared times dA. Note that, just like area, the area moment of inertia is always positive, and it has the unit of length to the fourth power. Sometimes you may want to find out the area moment of inertia about a point, say point O, when indeed we are trying to find the area moment of inertia about a z-axis that is perpendicular to the xy plane and passes through point O. The perpendicular distance from the differential element to the z-axis is r, and according to the same definition, Iz equals to the integration of r squared dA. But because x, y, and r are the three sides of the right triangle, therefore, according to the Pythagorean theorem, r squared equals to x squared plus y squared. Therefore, Iz also equals to the integration of s squared plus y squared dA, which equals to simply Iy plus Ix. And this is normally known as Jo. So in a 2D representation, when you see J, the polar moment of inertia about a point O, that means actually the area moment of inertia about an axis that is perpendicular to this plane and passes through this point O. If the area moment of inertia about an axis is known, you can find the radius of gyration about the same axis by taking the square root of I over the total area A. You can find the radius of gyration about any given axis, but normally it works the other way around. You are provided with the radius of gyration so that you can quickly calculate the area moment of inertia about a given axis. I equals to area A times k squared. Note that k is known as the radius of gyration because it has the same unit as a radius, which is the unit of length. A very useful and important theorem is the parallel axis theorem. For an area, if you know the position of its centroid, point C, let's say there is an arbitrary axis that passes through its centroid, axis A prime. And if you know the area moment of inertia about this axis, IA prime bar, then for another axis that is parallel to A prime, say axis A1 that has a perpendicular distance d1 from axis A prime, then the moment of inertia of this area about this new axis A1 can be calculated by the parallel axis theorem to be IA prime bar plus A, which is the area, times d1 squared. Or if there's another axis that is also parallel to A prime, axis A2, that has a distance d2 from A prime, then the moment of inertia about this axis A2 can also be calculated through the parallel axis theorem to be IA prime bar plus, again, area A times d2 squared. Therefore, using parallel axis theorem, you can quickly calculate the moment of inertia of the area about a parallel axis. As you can probably tell from these two equations, This I prime bar, the moments of inertia about the centroidal axis, is always the smallest among any parallel axis, which tells you that if this area is going to rotate about its centroidal axis, it will provide minimum resistance. As an example, imagine this ballet dancer spinning about her own centroidal axis, and then imagine you're trying to rotate her entire body about an axis that is further away. Which situation is easier, or which situation provides minimum resistance? The answer should be when she is rotating about her own centroidal axis, because the moment of inertia calculated about the centroidal axis is always the smallest among all its parallel axes. Now let's look at an example to see how we can use the equations to calculate the area moment of inertia. In this example, we need to determine the area moment of inertia of this rectangle about its centroidal axis, x-axis and y-axis. We follow this equation to find the area moment of inertia about the x-axis. We start with a differential element with sides dx and dy located at an arbitrary position x and y. Its area dA is dx times dy. We plug it into the equation and then do the integration. We must integrate with two variables because this rectangle has width of b and height of h. Along the y direction, we integrate from negative half an h to positive half an h, and along the x direction, we integrate from negative half a b to positive half a b, and eventually we get 1/12 bh to the third power. To avoid integration with two variables, alternatively, we define our differential element to be this horizontal strip with height of dy. The perpendicular distance from this differential element to the x-axis is a uniform y. Its area equals to the width b times the height dy, and we plug it into the equation, and we only need to integrate with one variable y from negative half an h to positive half an h, and eventually we get the same answer for the area of moment of inertia about the x-axis, 1/12 bh to the third power. Before we move on to the area moment of inertia about the y-axis, due to the symmetry of the rectangle, what do you think Iy should be? For Iy, we define our differential element to be this vertical strip with width of dx. Again, the perpendicular distance between this differential element to the y-axis is a uniform x. And the area equals to height times width h dx. We plug it into the equation, and eventually we get the area moment of inertia about the y-axis equals to 1/12 hb to the third power. Does this agree with what you originally guessed? Let's look at another example. We need to find the area moment of inertia of this circular area with a radius of r about its centroidal axis, x and y, as well as its polar moment of inertia about its center, point C. Let me remind you again, polar moment of inertia about point C is actually the area moment of inertia about a z-axis that is perpendicular to the xy plane and passes through point C. For this example, if we define our differential element as a square again, it will make the calculation very complicated. Alternatively, we define our differential element to be this thin ring that is located at a distance small r away from the center of the circle, and it has a thickness of dr. Therefore, the area of this differential element dA equals to the circumference 2 pi r times dr. Because this differential element has a uniform distance from the center, point C, therefore it is easier to first find the polar moment of inertia, Jc, which equals to the integration of r squared dA, and it equals to 1/2 pi r to the fourth power. Before we move on, I want you to pause again and think. Since polar moment of inertia equals to Ix plus Iy, and again, because of this symmetry of this circular area, What do you think Ix and Iy should be? Let's start with Ix. To find the differential element for Ix, let's draw two lines from the center with a small angle d theta. These two lines intercept with the thin ring that we defined earlier, and this is now our differential element. The perpendicular distance of this differential element to the x-axis, y, can be determined through trigonometry to be r sine theta. And if we zoom in on this differential element, the two sides are dr, which is the thickness of the ring, and r d theta, which is the length of the arc. We can approximate it as if it's a rectangle and determine its area dA to be r d theta times dr, and we plug it into the equation and integrate with two variables, theta and r. We integrate theta from 0 to 2 pi and r from 0 to capital R, the radius of the circular area, and we get Ix equals to 1/4 pi r to the 4th power. And because of the symmetry of the circle, this also equals to Iy, the area moments of inertia about the y-axis. Does this agree with what you initially guessed? Just like the centroid location of regular shapes, the area moment of inertia of regular shapes is also common knowledge and can be easily found either online or from your engineering textbook or handbooks. Once again, as an example, this is a screenshot of a page from Wikipedia. This is very useful, and I will show in the next video how you can use this available information to determine the moment of inertia of more complicated composite areas.